In this video, we're going to introduce the idea of a power series. Generally speaking, a power series is a type of series whose terms involve some variable, usually x. More specifically, the terms of a power series are going to involve powers of the variable x. For a particular example of a power series, we can consider the sum from n equals 0 to infinity of x to the nth power. We can find the first several terms of this series by starting with n equal to 0 and substituting that into the form of our term for n, and then moving on to n equal 1, n equal 2, and so forth. The first term here, notice, is n equal to 0. This will be standard for all power series that we will typically start at 0 for our indexing. And so here, when we let n equal to 0, we get x to the 0 power as our first term, which would be 1, and then x to the first power, which would be x, and so on through x squared, x cubed, x fourth, and so on forever. The key thing that is different about this series is that instead of raising a fixed number to the nth power like we would in a standard geometric series, here x is representing a variable that we can then substitute some value in for to obtain a specific infinite series. To make this notion a bit more precise, we're going to consider the following two definitions. A series of the form sum n equals 0 to infinity of c sub n x raised to the n is going to be called a power series centered at x equal to 0. This series will, when written out in as the sum of terms, will have the form c sub 0 plus c sub 1 x plus c sub 2 x squared, etc. Each of the c's, c0, c sub 1, c sub 2, and so forth, all of those are just representing any real number that we like, and x is our variable for our power series. Alternatively, we have a series of the form sum n equal to 0 to infinity of c sub n times the quantity x minus a raised to the nth power. And we're going to refer to this as a power series centered at x equal to a. So here, each of the c's will represent real numbers, just like in the power series centered at 0. X will be our variable for our power series, and a is another constant, in this case, that the center of our power series. Notice in particular that in the definition for the power series centered at x equal to a, if we let x equal to 0 and simplify each of the expressions in parentheses, they'll each, of course, just become x to the various powers, and we get the definition at the top of the screen, the power series centered at 0. And so these really aren't two separate definitions, but rather the first is a specific case of the second. However, we will use power series centered at 0 so much that it is worth having that power series set aside as a special case like this. It is worth noting that in both of these definitions, our power series will start at n equal to 0, not n equal to 1 like we might be accustomed to with most series. And that's actually quite important because that means our first term in each of our power series is going to be a constant that does not involve the variable x. To see some concrete examples of power series, we start by looking here at 3 different examples of power series centered at x equal to 0. We know each of these are centered at 0 because the variable term is x to the n and not x minus some constant to the nth power. Our first series is the one that we looked at earlier in this video, n equal to 0 to infinity of x to the n, which we know begins as 1 plus x squared plus x cubed, and so on. Here, the coefficient of each of the terms of our series is simply 1. And so if we wanted to identify c sub n in this particular series, we would see that c sub n is equal to 1 for every value of n. So in this example, the coefficients are constant, in this case always 1. But that's not typical for power series. Often, these coefficients will involve the number n. Our second example here is the sum n equals 0 to infinity of x to the n over n factorial. By starting with n equal to 0 and substituting values of n into our formula, we obtain a sum that begins as 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. Notice here that we are using a very standard convention that 0 factorial is always going to equal 1. This is used in the very first term when we want to find that the n equals 0 term is in fact 1. If 0 factorial were defined otherwise, then the first term here would be different. But in almost all instances, this is what we want whenever we need to consider 0 factorial. So you can take this as a convention for any example that involves series or power series. In this case, our coefficients are no longer constant because they change for each term. And we can see from our general term that the coefficient in front of x to the n is going to be 1 over n factorial. And so this is going to be our value of Cn in this particular power series. And so if we want to know the coefficient in front of, say, x to the 10th power, this tells us that it's going to be 1 over 10 factorial. Our third example is the sum n equals 0 to infinity of 2 to the n times x to the n. And again, by just letting n equal to 0 and then taking on subsequent values and substituting them into our term of our series, we obtain a sum that begins 1 plus 2x plus 4x squared plus 8x cubed, and so on. And we see here that our nth coefficient is going to be 2 to the n. So again, if we want the coefficient of x to the 10th power, we can see that it's going to be 2 raised to the 10th power. In this example, we look at a couple power series that are centered at values other than 0. In our first example, we have the sum n equals 0 to infinity of the quantity x plus 3 raised to the nth power. And the first several terms of that sum are 1 plus x plus 3 plus x plus 3 squared plus x plus 3 cubed, and so on. Here we can see that all of our coefficients are going to be 1, just like they were in one of the previous examples. We have no constants in front of the x plus 3 to the n here, so all of our coefficients will be 1. And for our center, we're going to consider that expression x plus 3, but we do need to write it as x minus a constant, and so here this would be x minus negative 3, by thinking of addition as subtracting a negative. And so from this representation of that expression, we see that our center, A, is going to be the number negative 3. So here, the important fact is that the center is always the value of A, where we have x minus A here in our expression. And so if we have x plus a number, the center will actually be the negative of that value, like it is here. Our second example is the sum n equals 0 to infinity of x minus 2 quantity to the n divided by n plus 1 times 3 to the n. Here our coefficient c sub n will involve the number n, and it's going to be the number with 1, or n plus 1 times 3 to the n in the denominator with 1 in the numerator. So this is the number that we're multiplying x minus 2 to the n by in order to get our terms. Also, the term that we're raising to the power that involves the variable is x minus 2, and so we see that our center here is positive 2 because our expression already has the form x minus a constant, and that constant turns out to be our center of our power series. Now that we've seen several examples of power series, we can think about how we might analyze them. So let's start by considering just a general power series, either of the form c sub n x to the n, so a power series centered at 0, or a power series of the form c sub n x minus a quantity to the n, which would be a power series centered at some number a. Thinking about this general power series, we can substitute some real number in for the variable x. And when we do that, we get an actual series resulting from this. It's no longer a power series because there's no longer a variable involved since we've replaced the variable with a constant. And so we get a standard infinite series, and we know that those could converge or diverge. And moreover, it is often the case that for certain values of x that we substitute in, we might get a convergent series, and for other values of x substituted into the same power series, we might get a divergent series. For a simple example of this behavior, let's consider the series n equals 0 to infinity of x to the n. When we substitute a specific value in for x, notice that we're going to obtain a geometric series. And we know simply by looking at the ratio of the geometric series whether it will converge or diverge. And so if we substitute in 1/2 for x, as in the example on the right, we'll get the sum n equals 0 to infinity of 1/2 to the n. And that is a geometric series with ratio of 1/2. And we know when the ratio is 1/2, that the geometric series will converge. On the other hand, if we substitute the number 3 in for x, like the example on the right, we'll get the sum n equals 0 to infinity of 3 to the n, and that is a geometric series with a ratio of 3, and that we know will diverge. And so here, depending on the value of x that we pick, we might obtain a convergent series or a divergent series. For this particular example, we actually know which x will produce a convergent series and which will produce a divergent series because we know exactly how the geometric series behaves. But for a general power series, we'll have to typically analyze this. And so one of the next steps in studying power series is to look at how to determine for which values of x the series will converge and for which values of x they'll diverge.